Tonight, one of the most famous stars in the sky is changing again. Betelgeuse, the red shoulder of Orion, has dimmed, brightened, and stirred new questions among astronomers. Is this giant star moving closer to its final explosion, or are these signs part of its normal restless life? In this video, the evidence is followed slowly, from the distant sky to the hidden core. Like the video, subscribe to the channel and stay with this quiet journey into Betelgeuse. High above Earth, within the dark span of the winter sky in the northern hemisphere, Betelgeuse glows with a muted orange-red light near the shoulder of Orion. The star appears large in memory and tradition, though to the eye it remains only a point of light among many others. Ancient observers across many regions notice its changing brightness long before telescopes exist. In some years it shines more strongly than nearby stars. In other years it fades until the pattern of Orion seems altered. The variation happens slowly enough that it enters seasonal memory rather than sudden alarm. Modern astronomy later confirms that Betelgeuse truly changes in brightness over time. The star is not steady. Its surface and outer layers shift, expand, cool, and brighten in repeating but imperfect rhythms. From Earth, Orion rises during the colder months for many northern observers and during warmer months in much of the southern hemisphere. 3 bright stars form the belt at the centre. Betelgeuse marks one upper corner of the figure, while Rigel shines blue-white at the opposite lower side. The contrast between the 2 stars becomes one of the clearest visible examples of different stellar temperatures. Rigel burns hotter and appears pale blue-white. Betelgeuse is cooler at its visible surface and radiates a softer orange-red glow. Even without instruments, the colour difference reveals that stars are not identical bodies. They exist in different stages of development and lose energy in different ways. Modern telescopes no longer see Betelgeuse as a simple point. Large observatories on Earth and in orbit resolve a broad disk of light. The star appears immense. If placed at the centre of the solar system, its outer atmosphere would stretch beyond the orbit of Mars and perhaps near Jupiter, depending on how its edge is defined. Yet despite its vast size, the star is diffuse compared with the Sun. Its outer layers are spread thinly across a huge volume. Density decreases greatly toward the outer atmosphere. Matter there drifts more like a thinning cloud than a sharply bounded surface. Astronomers classify Betelgeuse as a red supergiant. A supergiant is a very large and luminous star formed from a star that begins with far greater mass than the Sun. Over millions of years, such stars exhaust hydrogen fuel in their cores and expand enormously. Their surfaces cool while their total light output remains powerful. Betelgeuse belongs to this late stage of stellar evolution. Observations indicate that it is relatively young by stellar standards, perhaps only around 10 million years old. Massive stars consume fuel rapidly. Their lives unfold quickly compared with stars like the Sun, which may remain stable for billions of years. Across the 20th and 21st centuries, astronomers monitor Betelgeuse with increasing precision. They measure brightness, surface motion, chemical signatures, temperature changes, and the movement of gas surrounding the star. Instruments sensitive to infrared light reveal structures invisible to human eyes. Radio telescopes detect matter flowing outward. Space observatories record pulses of energy from different layers around the star. Each observation adds detail to an object that once seemed distant and simple. Interest in Betelgeuse grows especially strong because astronomers know that red supergiants eventually end in supernova explosions. A supernova is the violent collapse and destruction of a massive star after nuclear fuel can no longer support the core against gravity. Such events briefly outshine entire galaxies. Heavy elements formed during stellar life, and during the explosion spread into space. Future stars, planets, rocks, oceans, and living bodies later form partly from this material. Betelgeuse, therefore, becomes more than a bright point in Orion. It becomes an example of how matter changes form across cosmic time. Yet the timing of any future explosion remains uncertain. Observations indicate that Betelgeuse is advanced in age compared with hotter blue stars nearby, but no evidence proves that collapse is imminent on a human timescale. In astronomy, imminent can still mean tens of thousands or even hundreds of thousands of years. Scientific caution remains important because many processes deep inside the star cannot be observed directly. Astronomers rely on models built from physics, surface measurements, and comparisons with other massive stars. These models improve over time but remain incomplete. The attention surrounding Betelgeuse increases sharply during the event now called the Great Dimming. Between late 2019 and early 2020, the star fades dramatically. Many casual skywatchers notice the change without instruments. Reports spread widely. Some imagine that the long-expected supernova may be close. Observatories around the world turn toward Orion. Data from telescopes on Earth and in orbit later show that the fading likely results from a combination of surface cooling and a cloud of dust released by the star itself. The event demonstrates how active and unstable the outer layers of a red supergiant can become without signaling immediate destruction. The night sky above Earth remains otherwise unchanged during these years. Orion continues to rise and set with the seasons. Betelgeuse still glows in its familiar place, though never with complete steadiness. Its light travels for centuries before reaching human eyes. The photons entering telescopes tonight leave the star long before modern astronomy exists. In this way, every observation becomes partly historical. The star seen from Earth is always a delayed image shaped by distance and time. Around the world, observatories continue their patient work. ESO telescopes in Chile record changing surface patterns. NASA instruments examine temperature shifts and surrounding gas. Amateur astronomers contribute brightness measurements gathered night after night across many years. Large data sets accumulate slowly. The story of Betelgeuse emerges not from sudden revelation but from repeated careful watching. Against the cold darkness beyond Earth's atmosphere, the star remains quiet to the unaided eye. No explosion appears. No violent burst interrupts Orion. Only gradual variation continues, subtle and persistent. The sky holds its shape while astronomers study the faint evidence carried in light. Between Earth and Betelgeuse lies a great depth of interstellar space. This region seems empty from a human point of view, yet it contains thin gas, small grains of dust, magnetic fields, and faint radiation moving in many directions. The distance is so large that ordinary measures become difficult to imagine. Astronomers estimate that Betelgeuse is several hundred light-years away, with modern values commonly placed near 500 to 650 light-years. A light-year is the distance light travels in 1 year. The uncertainty remains larger than for many nearby stars because Betelgeuse is bright, huge, changing, and surrounded by material that makes precise measurement difficult. The light that reaches Earth from Betelgeuse begins its journey at the star and crosses the space between stars without needing a medium. It travels through darkness at a constant speed in vacuum. During the journey, most of it moves freely. Some light interacts with dust grains, and some is absorbed or scattered along the way. These effects are small but important. Astronomers must account for them when estimating how bright Betelgeuse truly is. The brightness seen from Earth depends on both the star's real power and the long path the light has taken. Distance is central to nearly every question about Betelgeuse, a star's true luminosity, meaning its total energy output, cannot be known from apparent brightness alone. A nearby dim star can look similar to a distant bright star. Betelgeuse looks bright because it is intrinsically luminous, not because it is especially close by stellar standards. Still, its exact luminosity depends on distance. A somewhat larger distance means a greater true energy output. A somewhat smaller distance means a lower one. This affects estimates of its size, age, mass, and evolutionary stage. Astronomers measure stellar distances using parallax when possible. Parallax is the tiny apparent shift in a nearby star's position, caused by Earth moving around the Sun. As Earth travels from one side of its orbit to the other, a nearby star seems to move slightly against the more distant background. The shift is extremely small. For Betelgeuse, the task is especially demanding because the star is not a sharp point. Its surface is broad, uneven, and changing. The center of its light may shift as bright patches grow and fade. This makes the apparent position less stable than that of a smaller, quieter star. Space missions have improved distance measurements for many stars. The European Space Agency's Gaia mission measures positions and motions for a vast number of stars with great precision. Yet Betelgeuse remains difficult even for such advanced instruments. Its brightness can saturate detectors, and its extended atmosphere complicates the clean measurement of position. Radio observations and other methods are therefore used alongside optical measurements. Each method carries its own uncertainty. The result is not a single perfect number, but a range supported by different lines of evidence. The space between Earth and Betelgeuse also contains the broader structure of the Milky Way. Both the Sun and Betelgeuse belong to the same galaxy, within a spiral disk filled with stars and gas. The path from one to the other does not cross a simple blank gap. It passes through the local galactic environment, where sparse clouds of atoms and dust drift slowly. These clouds are far thinner than any air on Earth, yet over hundreds of light years they can affect starlight in measurable ways. Dust tends to block and redden light, making stars appear slightly dimmer and redder than they would appear without it. This reddening matters because Betelgeuse is already red by nature. Its surface temperature is much cooler than that of blue or white stars, so much of its visible light is orange and red. Astronomers separate the star's natural colour from the reddening caused by interstellar dust. They compare light at different wavelengths, from visible to infrared. Infrared light passes through dust more easily than blue light. By studying several wavelengths together, researchers estimate how much dimming belongs to the space along the line of sight, and how much belongs to the star itself. The long distance also means that every present observation is delayed. When observers on Earth record a change in Betelgeuse tonight, they are recording light that left the star centuries earlier. The star's current physical state, at this same moment in space, is not directly visible from Earth. This delay does not weaken the science, because all astronomical observation beyond the solar system works in this way. It simply means that the visible Betelgeuse is always Betelgeuse, as it was when the light began its journey. The idea of delay often shapes public interest in the star's possible explosion. If Betelgeuse were to collapse and explode, the event would become visible on Earth only when the light and other signals arrived after crossing the distance between. Until then, Earth would remain unaware of that event. However, observations available now show no confirmed sign that such an explosion is already on its way. The measured light displays variability, surface activity, dust formation. and atmospheric motion, all of which are expected for a red supergiant. Across the interstellar gap, the star's changing light becomes a message carried without sound. It contains information about temperature, chemical elements, motion, and dust, spectroscopy. The study of light separated into its colors reveals dark and bright features produced by atoms and molecules. These features shift slightly when gas moves toward or away from Earth. They broaden when material is turbulent or hot from a great distance. Astronomers read these fine patterns and reconstruct conditions around the star. The space itself remains silent, thin, and cold. No wind like Earth's atmosphere moves through it. No air carries sound from Betelgeuse, only radiation, particles, and fields cross the distance. The orange light reaches telescopes after passing through this sparse region, softened by dust, delayed by space, and altered by the star's own restless outer layers. From Earth, Betelgeuse appears near and familiar in Orion, yet the path to it is vast. The first inward step toward understanding the star is therefore not at the star itself, but in the quiet interval that separates the observer from the source of the light. Within the constellation Orion, Betelgeuse belongs to a region of the sky that contains many bright, young, massive stars. Orion is not only a familiar pattern seen from Earth, it is also a direction toward a rich part of the Milky Way, where stars have formed from large clouds of gas and dust. Some of these clouds remain visible through telescopes as glowing nebulae. Others are darker and colder, seen most clearly by the way they block or emit infrared light. Betelgeuse stands apart from the central belt and sword of Orion, yet its place in this wider stellar setting helps explain why it is massive, luminous, and short-lived. The Orion region contains stars at different stages of life. Some are still forming inside dense clouds, some are young, hot, and blue-white, burning fuel rapidly. Others have already moved away from their birthplaces. Massive stars do not live long enough to wander as far as older. Smaller stars often do. Their brief lives keep them linked, in broad terms, to the regions where they formed. Betelgeuse is one such massive star. Its orange-red colour shows that it has already changed greatly from its earlier, hotter state. It has expanded and cooled at the surface, becoming a red supergiant while many nearby massive stars remain blue and compact by comparison. Orion also includes a structure known as the Orion Molecular Cloud Complex. A molecular cloud is a cold, dense region where atoms bind into molecules and where new stars can form. The Orion Nebula is the most famous visible part of this complex. It glows because hot young stars energize nearby gas. Farther across the region, darker clouds and faint arcs show that star formation has shaped the surrounding space for millions of years. Betelgeuse is not embedded within a bright birth cloud now. It has moved through space since its formation. Its present location is a stage in a longer motion through the galaxy. The star's motion can be measured across the sky and along the line of sight. Across the sky, it has proper motion, a slow change in position against the distant background. Along the line of sight, its light shows a radial velocity, meaning motion toward or away from Earth. These measurements indicate that Betelgeuse travels through its surroundings rather than resting inside a fixed pattern. The constellation is only an apparent arrangement from Earth. Its stars lie at different distances and move in different directions. Orion's shape is stable over human lifetimes, but it is not a permanent structure. Betelgeuse is often associated with the larger population of young massive stars in the Orion area. Astronomers study whether it may have formed in an association, a loose group of stars born from related gas clouds. Stellar associations spread out with time because their members are not tightly bound by gravity. The stars drift apart while retaining clues in their motions and ages. Betelgeuse's age and motion have led researchers to compare it with groups in Orion. Though exact membership remains uncertain, its current position does not by itself reveal a single birthplace. The evidence must come from motion, distance, age, and chemical composition together. The environment around Orion is shaped by past generations of massive stars. When such stars shine, they produce strong radiation and winds. When they die, they can explode as supernovae. These events stir gas, compress clouds, and create cavities in the interstellar medium. A medium, in this use, means the thin material spread between stars. Orion contains signs of this shaping. Large loops and shells of gas suggest that winds and earlier explosions have pushed material outward. Betelgeuse now moves within a wider region already disturbed by stellar activity. Its own wind adds a smaller, local contribution to this pattern. Nearby on the sky, stars such as Rigel, Bellatrix, and the belt stars create a striking visual frame, but they are not all close neighbours in three-dimensional space. Rigel is a blue supergiant, very luminous and hot, but it lies at a different distance and follows a different evolutionary path. The belt stars are also hot and massive, shining with blue-white light. Their apparent alignment is a perspective effect from Earth. Betelgeuse shares the visual figure, yet its physical relation to each visible star must be measured, not assumed. Astronomy separates the apparent map from the actual spatial arrangement. This distinction matters because public descriptions often make Orion seem like a single object. In physical terms, it is a direction containing many objects at varied distances. Betelgeuse is a foreground or mid-distance member of this view, depending on the comparison star. The nebulae, dust clouds, and stellar groups behind and around it form a layered scene. Light from each layer reaches Earth along the same general line of sight. Telescopes and distance measurements separate these layers and give them depth. Betelgeuse's colour also changes the visual balance of Orion. Most bright, massive stars in the region appear blue-white because their surfaces are hot. Betelgeuse appears red because its visible surface is much cooler. This difference marks a late evolutionary state, rather than a different birth environment alone. A massive star can begin hot and blue, spend most of its life fusing hydrogen in its core, and later expand into a red supergiant. The red colour does not mean the star is weak. It means the energy comes from a very large area at a lower surface temperature. Total light output remains enormous. In the wider Orion setting, Betelgeuse is therefore both part of a young massive star landscape and distinct from much of what surrounds it. The blue stars and glowing gas show active or recent star formation. Betelgeuse shows the later life of a massive star that has moved beyond its main stable phase. The same region of the galaxy can contain both beginnings and endings because massive stars evolve quickly. Gas clouds form stars. Young stars heat gas. Older massive stars lose matter. Each process changes the local environment. Observations of Orion continue across many wavelengths. Visible light reveals bright stars and glowing nebulae. Infrared light traces warm dust and stars hidden in clouds. Radio observations show cold gas. Ultraviolet and X-ray observations reveal hot young stars and energetic regions. Betelgeuse is studied within this layered view, but the section of space immediately around it is only one part of the larger field. The star's known variability, size, and red colour gain meaning when placed among the younger, hotter stars and the cloud structures of Orion. From Earth, The constellation remains a quiet pattern of points and soft mist. Within that pattern, Betelgeuse marks a late stage of massive stellar life in a region where massive stars are common. Its place is not isolated, but neither is it simply tied to every bright star nearby in the sky. It belongs to a larger galactic neighbourhood shaped by gas, dust, birth, motion, and age. The outer setting around Betelgeuse is therefore a measured environment, not only a mythic figure, and it gives the star its broader scientific frame. Around Betelgeuse, beyond the bright disk that telescopes measure as the star itself, there is a broad and uneven region of dust and gas. This surrounding material is not part of the empty background between stars alone. It belongs in large part to matter that Betelgeuse has already released from its own outer layers. A red supergiant does not hold its atmosphere tightly in the way a smaller, denser star does. Its surface gravity is weak across its enormous radius. Gas can rise far from the visible surface, cool, form simple molecules, and drift outward. Over time, this lost material creates a faint extended environment around the star. Infrared observations reveal this region more clearly than visible light. Dust grains absorb energy from the star and radiate at longer wavelengths. Infrared light is well suited to tracing such warm dust, because the grains are too cool to shine strongly in ordinary visible light. Telescopes operated by NASA, ESA, ESO, and other observatories have shown arcs, clumps, and uneven structures around Betelgeuse. These structures are not arranged as a perfect sphere. They show that mass loss from the star is irregular. Some directions contain more material than others. Some regions appear shaped by the star's movement through surrounding space. Dust near Betelgeuse forms only where gas has cooled enough for atoms and molecules to join into tiny solid particles. The star's visible surface is too warm for stable dust, but farther out, conditions become cooler. In these outer zones, elements such as silicon, oxygen, aluminum, and other heavy atoms can become part of mineral grains. These grains are extremely small, far smaller than sand. Yet together they have strong effects on light. They can block, scatter, and re-radiate radiation from the star. A cloud of such grains can make part of Betelgeuse appear dimmer from Earth if it passes across the line of sight. The material around the star also carries a record of earlier changes. Betelgeuse does not lose mass at one perfectly steady rate. Observations indicate that its outer atmosphere produces outflows that vary with time and direction. Large convective motions, pulsations, and atmospheric disturbances can send extra gas into space. Once outside the star's stronger heating, some of that gas cools and contributes to dust. The arcs and shells around Betelgeuse may therefore be traces of earlier episodes of mass loss. They are like faint layers left by a changing wind, though much less sharp and regular than rings drawn on a page. One notable feature seen in infrared studies is a bow-shaped structure ahead of Betelgeuse's motion. A bow shock forms when a star's wind meets the material between stars while the star moves through it. The situation is similar in shape to water piling gently before a moving boat, though in space the material is thin gas and dust rather than liquid water. Betelgeuse's wind pushes outward. The surrounding interstellar material pushes back as the star travels through it, where these flows meet. Matter can become compressed and warmer, making it more visible in infrared light. The bow structure helps astronomers estimate the motion of the star and the strength of its wind. Farther from the star, the surrounding material becomes more blended with the interstellar medium. The boundary between matter lost by Betelgeuse and matter already present in space is not always simple. Gas mixes, dust drifts, radiation changes grain temperatures. Astronomers use shape, motion, temperature, and chemical clues to separate these components. The results remain partly uncertain because the material is thin and faint. Still, the presence of a circumstellar environment, meaning matter surrounding the star itself, is well established. This dusty region matters for interpreting Betelgeuse's brightness. When the star fades, the cause may not be only a change in the star's surface. Dust along the line of sight can reduce visible light. During the Great Dimming, observations showed that new dust likely formed after material was expelled from part of the star. This dust cooled and blocked some of the visible light reaching Earth. The wider dust environment shows that such events are not unexpected for a red supergiant. The star is already surrounded by the products of its own mass loss. The surrounding dust also affects estimates of the star's temperature and luminosity. Some of the light emitted by Betelgeuse is absorbed by grains and re-emitted in infrared. If only visible light is considered, part of the star's energy budget is missed. Astronomers therefore measure across a broad range of wavelengths. They combine visible, infrared, and sometimes radio observations to form a more complete account of the star's output. The dust is not a minor decoration around the star. It is part of the system being measured. The gas mixed with the dust contains molecules that can be detected through their spectral signatures. Molecules such as carbon monoxide and water vapor can exist in cooler parts of the extended atmosphere and surrounding region. Their presence indicates that the environment is not uniformly hot. Temperature changes strongly with distance from the visible surface. In places where gas is dense enough and cool enough, molecules survive. In thinner or more strongly irradiated regions, they break apart or become harder to detect. These chemical traces help map the conditions in the outer material. The dust and gas around Betelgeuse move slowly compared with light, yet steadily over time. A wind of material flowing outward from a red supergiant may travel at speeds measured in kilometers per second. Over centuries and millennia, even such moderate motion carries matter far from the star. The result is a large, faint envelope that expands into surrounding space. This process reduces the star's mass before any final collapse occurs. How much mass Betelgeuse has already lost remains an important part of modelling its future evolution. There is no evidence that the existence of dust around Betelgeuse means an explosion is about to occur. Dust formation is a known feature of evolved red supergiants. It shows that the outer layers are active and unstable, but not that the core is at the final moment before collapse. Observations indicate ongoing mass loss, changing clumps, and interaction with surrounding gas. It remains uncertain how these outer structures relate in detail to deeper internal processes. The dust can reveal the behavior of the star's outer regions, but it cannot directly show the state of the hidden core. In the wide space around Betelgeuse, the star has already begun returning matter to the galaxy. The dust grains are small, the gas is thin, and the structures are faint, yet together they form a visible record of stellar aging. Light from the red supergiant warms them. Motion shapes them. Earlier outflows leave uneven marks around the star. This outer material is the first physical layer belonging to Betelgeuse itself, a quiet field of lost matter surrounding a changing star. Closer to Betelgeuse, inside the wider dust field but still outside the main visible body of the star, the outward flow becomes the stellar wind. A stellar wind is gas leaving a star and moving into space. In Betelgeuse, this wind is not like a steady stream from a small, compact source. It comes from an enormous, cool, unstable outer region where gravity is weak and matter is only loosely held. The wind carries atoms, molecules, and dust-forming material away from the red supergiant. Over long periods, it changes the star itself by slowly reducing its mass. The wind begins as gas lifted from the outer atmosphere. In a red supergiant, the surface layers are broad and restless. Pressure waves, large rising currents, and radiation help push material upward. Once gas reaches enough distance from the star, it can cool. Molecules can form. Dust grains may begin to condense. Radiation from Betelgeuse then pushes on these grains and helps draw more material outward. The process is complex because gas and dust do not always move together perfectly, and because the star does not release matter equally in all directions. Measurements show that Betelgeuse loses mass at a significant rate compared with the Sun, though estimates vary. The exact rate depends on assumptions about distance, wind speed, dust content, gas density, and geometry. Astronomers usually describe the loss in solar masses per year, but the amount is small compared with the whole star during a single year, over thousands of years. However, the loss becomes important. A massive star approaching the end of its life may shed a large part of its outer envelope before collapse. Betelgeuse is already participating in this slow return of matter to space. The wind is detected in several ways. Radio telescopes observe emission from atoms and molecules in the gas. Infrared telescopes observe dust warmed by the star. Spectroscopy shows lines that shift and broaden as material moves. These signals reveal that the wind is cool compared with the deep layers of the star and that it expands outward at modest speeds. The wind is not a blast. It is a persistent flow, shaped by the size of the star and by weak gravity at its surface. The speed of the wind is low compared with the fast winds from hot blue stars. A hot massive star can drive a rapid wind through intense ultraviolet radiation. Betelgeuse, with its cooler surface, drives a slower and denser wind. This slower movement allows material to remain near the star longer and to form dust in favourable conditions. The wind therefore becomes both a movement of gas and a factory for small grains. Those grains later join the surrounding dust field and contribute to the broader environment around the star. The wind is uneven. Observations indicate clumps, arcs, and changing structures rather than a smooth sphere. This unevenness likely reflects conditions at the star's outer layers. If one region of the surface is brighter, cooler, more extended, or more disturbed than another, it may send out more material. Large convective cells can raise gas from inside the star to the outer atmosphere. Pulsations can help lift the atmosphere as the star expands and contracts. The wind records these motions after the gas leaves the visible surface. Because the wind carries material outward, it also carries chemical evidence. Betelgeuse has already changed its surface composition through internal mixing. Material processed inside the star can reach the outer layers and then leave through the wind. Spectral studies of red supergiants often examine elements and molecules to understand this mixing. In Betelgeuse, the wind may include signs of material altered by earlier nuclear burning and later brought toward the surface. The evidence is indirect, but it helps connect the outer flow to the star's life history. The wind also shapes the space immediately around Betelgeuse by pushing against surrounding gas. Near the star, the wind expands freely. Farther out, it meets material in the interstellar environment and becomes compressed or deflected. The bow-shaped structures seen farther away are the large-scale result of this interaction. In the wind zone itself, the gas is still mainly controlled by the star's outflow. Density decreases with distance because the same material spreads over a larger volume. Temperature also changes as gas expands and cools, while radiation from the star continues to heat dust grains. The balance between gas and dust is important. Gas makes up most of the mass, while dust makes up a smaller fraction. Yet dust strongly affects light and radiation pressure. A small amount of dust can absorb visible and near-infrared light efficiently. When radiation pushes on dust grains, collisions and drag can transfer momentum to nearby gas. In this way, dust may help the wind escape. The details remain uncertain because conditions are difficult to reproduce exactly in models. Observations indicate that dust exists close enough to influence the flow, but the exact sequence of lifting gas, forming dust, and accelerating wind remains under study. The wind does not directly reveal whether Betelgeuse is about to explode. Mass loss is expected in red supergiants across long periods. A change in the wind can show that the outer atmosphere is active, but it does not by itself measure the state of the core. The core is hidden behind vast layers of gas. The wind belongs to the exterior, where motions can be dramatic without meaning that collapse is near. Scientific interpretation therefore remains careful. Observations indicate that Betelgeuse is losing mass and forming an extended outflow. It remains uncertain exactly how this mass loss changes the star's final evolution. The wind also complicates the definition of the star's edge. Unlike a planet or a solid body, Betelgeuse does not end at a sharp boundary. Its light-forming surface gives one useful radius, but gas continues beyond it. Molecules and dust appear farther out. The wind extends still farther, thinning into space. Each layer has a different meaning. The visible surface marks where much of the light escapes. The atmosphere marks surrounding gas still strongly tied to the star. The wind marks material moving away. This gradual transition makes Betelgeuse more like a glowing atmosphere than a firm sphere. Within this outward flow, the star's future material is already becoming galactic material. Atoms once held in the star's envelope drift away into the surrounding region. Some become part of dust grains. Some remain as gas. Over time, they mix with the interstellar medium. The wind is slow, broad, and persistent, and it shows the aging of a massive star in motion. It is not the final event, but it is part of the long preparation by which Betelgeuse loosens its outer layers and releases them into the quiet space around it. Inside the wind zone, closer to the star's bright body, Betelgeuse has an extended atmosphere that reaches far above the visible surface. This atmosphere is not a thin, smooth layer like a simple shell. It is broad, uneven, and changing. Gas rises and falls through it. Some regions are warmer, others cooler. Some parts appear more extended than others. The star's low surface gravity allows material to move outward to great distances before it either falls back, drifts away, or joins the stellar wind. In this region, Betelgeuse begins to lose the clear shape that smaller stars seem to have. The atmosphere of a red supergiant includes layers where atoms, molecules, and dust-forming material can exist at the same time in different zones. Nearer the visible surface, gas remains warm enough that many molecules break apart. Farther out, cooler pockets allow molecules to survive. Water vapor, carbon monoxide, silicon monoxide, and other molecules can leave marks in the star's spectrum. A spectrum is starlight spread into its colors, where atoms and molecules create patterns that reveal their presence. These molecular signs show that the atmosphere is not uniformly hot. It contains temperature differences across both height and direction. Observations with large telescopes have shown that Betelgeuse's atmosphere extends to several times the radius of the visible photosphere in some wavelengths. The photosphere is the layer from which most visible light escapes. Above it, gas can still be dense enough to absorb and emit light at infrared, radio, and ultraviolet wavelengths. Different instruments therefore see different apparent sizes for the same star. In visible light, one radius may be measured in radio light. Cooler gas farther out may make the star appear larger. This does not mean the star changes size from one instrument to another. It means each wavelength traces a different layer. The atmosphere is also asymmetrical. High-resolution images have revealed bright areas and dark areas on the disk of Betelgeuse. These patterns shift over time. Some may be linked to large convective cells beneath the surface. Others may be caused by clouds or temperature differences above the photosphere. The atmosphere can hide, soften, or alter the appearance of the surface below it. A bright patch may appear when hotter material reaches upward. A dim patch may appear when cooler gas or dust lies along the line of sight. The image changes because the star itself is in motion. In some observations, the outer atmosphere shows gas moving both inward and outward at the same time in different regions. This is expected for a body with large-scale pulsation and convection. Pulsation means expansion and contraction of stellar layers. Convection means transport of heat by rising and sinking gas. On Betelgeuse, these processes occur on enormous scales. A single moving region can be comparable in size to a large fraction of the star's visible disk. The atmosphere responds slowly in human terms over months or years, but quickly compared with the full life of a star. The extended atmosphere is sometimes described as a molesphere in studies of cool giant and supergiant stars. The term refers to a molecular sphere, a region above the photosphere where molecules are present. The name suggests a sphere, but in Betelgeuse the shape is not perfectly round. It is a useful concept for the molecular layer, not a rigid boundary. This region helps explain why the star's measured diameter and temperature can vary depending on method. Molecules absorb light in some wavelengths and emit in others. Their presence changes what telescopes record. The atmosphere also plays a central role in dust formation. Gas rising from the star must cool before solid grains can begin to condense. The extended atmosphere provides places where this cooling can happen. Material lifted high enough may reach temperatures suitable for grain formation. Once grains form, radiation from the star can push them outward. This connection between atmosphere and wind makes the atmospheric region a transition zone. It is still part of the star's influence. But it is also the place where some matter begins its departure. Recent studies have also examined whether a small companion star may influence the outer atmosphere or the observed brightness changes of Betelgeuse. Evidence has been discussed for a possible close companion, though its properties remain uncertain. Such a companion, if present, would be far fainter than Betelgeuse and difficult to detect directly beside the red supergiant's glare. Its gravity or light could affect measurements in subtle ways. Observations indicate patterns that may be consistent with an additional object, but the interpretation is not settled. The atmosphere of Betelgeuse itself is active enough that separating companion effects from internal stellar changes remains difficult. The possibility of a companion does not remove the known atmospheric variability of Betelgeuse. The star clearly has an unstable and extended outer atmosphere. It produces changing spectral lines, shifting brightness, and uneven images. A companion, if confirmed, would add another influence within the surrounding system. It would not mean that the star is about to explode. It would instead help explain some measured changes that have been hard to assign to a single cause. Scientific work in this region remains careful because the atmosphere, wind, dust, and any possible companion all overlap in observation. The atmosphere absorbs and reprocesses light from below. Photons leaving the hotter inner layers pass through gas that may scatter them, absorb them, or release them again at different wavelengths. This process changes the apparent color and brightness of the star. It also means that a dimming event can begin in the atmosphere without requiring a deep change in the core. A cloud, a cooling region, or a lifted mass of gas can alter what reaches Earth. The outer atmosphere is therefore a place where visible signs can be produced by shallow layers. Astronomers study this atmosphere with interferometry, a method that combines light from separated telescopes to see fine detail. This allows Betelgeuse's disk and nearby gas to be examined with much sharper resolution than a single telescope could provide. Infrared interferometry has been especially useful because cool gas and dust shine strongly at longer wavelengths. Radio measurements also trace the extended layers together. These methods show a star surrounded by a living envelope rather than a neat surface. In the extended atmosphere, the question of explosion remains distant from direct evidence. This region shows activity, but it belongs to the star's outer structure. It reveals mass lifting, cooling, molecular formation, and possible dust production. It shows that Betelgeuse is unstable in the normal way expected for a red supergiant. It does not show the hidden core's final state. Observations indicate that the atmosphere can change greatly over a short span of years. It remains uncertain how each atmospheric event connects with the deeper evolution of the star. Here the star becomes less like a fixed sphere and more like a vast breathing layer of gas. The outer atmosphere swells above the light-forming surface, filled with molecules, waves, clumps, and slow motions. It is close enough to Betelgeuse to carry the imprint of its heat, yet far enough outward for matter to cool and prepare to leave. The orange-red light seen from Earth passes through this region before crossing space, carrying with it the marks of a restless atmosphere around an aging massive star. Beneath the extended atmosphere, Betelgeuse reaches the visible surface that astronomers call the photosphere. This is not a solid surface. It is the layer where the gas becomes transparent enough for much of the star's visible light to escape into space. In a star like the Sun, the photosphere appears relatively sharp compared with the star's size. In Betelgeuse, the photosphere is more diffuse because the star is enormous and its outer gas is spread thinly. Still, it gives a useful boundary for measuring the star's apparent disk, temperature, and changing brightness. The photosphere of Betelgeuse is cool by stellar standards. Its temperature is commonly estimated near 3,500 degrees Kelvin, though the value changes with method and time. Kelvin is a temperature scale used in science, with 0 representing the lowest possible thermal state. Betelgeuse's visible surface is far cooler than the Sun's, yet the star shines with great power because the glowing area is immense. A cooler surface spread across a huge radius can produce far more total light than a smaller, hotter surface. This is why Betelgeuse can appear bright across hundreds of light years. The red-orange colour comes from this relatively low surface temperature. Hotter stars emit more blue and ultraviolet light. Cooler stars emit a larger share of their visible light in red and orange wavelengths, along with strong infrared radiation. Betelgeuse is therefore bright not only to human eyes, but also to instruments that detect infrared light. The photosphere gives the star its familiar colour, while the surrounding atmosphere and dust alter that colour slightly before the light begins its long journey outward. The photosphere is uneven. High-resolution observations show that Betelgeuse does not glow with the same brightness across its whole disk. Some areas appear brighter, others dimmer. These differences are likely tied to giant convection. Convection is the movement of heat by rising and sinking material. In the outer parts of a red supergiant, hot gas rises from deeper layers, spreads, cools, and sinks again. Because Betelgeuse is so large and its outer layers are so loosely held, the convective patterns can be vast. A few large cells may cover much of the visible surface rather than many small cells. These surface patterns change with time. A bright region may grow, fade, or shift. A cooler region may darken part of the disk. Since Betelgeuse is unresolved to the unaided eye, all of these changes blend into one point of light. The total brightness seen from Earth rises or falls as the surface and atmosphere change together. Modern imaging separates some of the surface structure, but not in the detail possible for nearby planets or the Sun. The star remains far away, and its disk is small in apparent size despite its physical immensity. The photosphere also moves. Spectral lines formed in this layer show gas rising and falling. Some lines shift toward shorter wavelengths when material moves toward Earth, and toward longer wavelengths when it moves away. This motion is not uniform across the star. Different regions can move in different directions. The surface is therefore not a smooth expanding or contracting sphere alone. It is a restless layer where local and global motions overlap. Pulsation changes the radius and brightness over time, while convection creates uneven patches. The apparent size of Betelgeuse has been measured with interferometry, which combines light from separate telescopes to produce very fine angular resolution. These measurements show that the star's diameter changes depending on wavelength and model, at visible and near-infrared wavelengths. The measured photospheric disk has been used to estimate a radius hundreds of times that of the Sun. The exact value remains uncertain because of distance uncertainty, atmospheric extension, and surface structure. A small change in distance changes the physical size inferred from the apparent disk. The photosphere is also a place where titanium oxide molecules strongly influence visible light. Titanium oxide absorbs light in broad bands in cool stars. These bands help astronomers classify red supergiants and estimate temperature. When the photosphere cools, titanium oxide absorption can strengthen, changing the star's apparent brightness in visible wavelengths. This effect became important in interpreting major dimming events. A cooler photosphere can appear much fainter in visible light even if the total energy output changes less dramatically. The visible brightness of Betelgeuse is measured on a magnitude scale. Magnitude is a traditional system in which smaller numbers mean brighter objects. Betelgeuse varies enough that its place among the brightest stars changes over time. It is usually one of the brighter stars in the night sky, but it can fade noticeably. This variation is normal for the star. It belongs to the class of semi-regular variable stars, meaning its brightness changes in patterns that are partly periodic but not perfectly regular. The photosphere is a major source of these changes. During periods of ordinary variation, the surface may warm and cool, expand and contract, and change its pattern of bright and dim regions. These changes alter the amount of visible light reaching Earth. They do not require a catastrophic event. A red supergiant's outer layers are naturally unstable because radiation, gravity, pressure, and convection are balanced only loosely. The photosphere reflects this balance. It is where internal energy finally becomes the visible glow. But it is also affected by motions from below and absorption from above. The surface gravity at the photosphere is very low compared with the Sun. Gravity depends on mass and radius, and Betelgeuse's radius is enormous. Even though the star is massive, its outer surface lies so far from the center that gravity is weak there. This weakness helps the atmosphere expand and allows gas to be lifted more easily. It also contributes to the broad, soft nature of the photospheric boundary. The star's light does not come from a neat shell, but from a thick transition region where opacity changes gradually. Opacity means how strongly matter blocks or absorbs radiation. In the photosphere, Opacity determines where light escapes. If gas becomes more opaque, light escapes from higher, cooler layers. If it becomes less opaque, light can emerge from deeper, warmer layers. Molecules, atoms, temperature, and density all affect opacity. In Betelgeuse, these factors vary across the surface and with time, so the apparent photosphere shifts. The star's visible edge is therefore partly a matter of wavelength and physical conditions, not a fixed material boundary. The photosphere does not show that Betelgeuse is about to explode. It shows that the star is cool, vast, variable, and late in its life. Its patches, temperature changes, and brightness cycles are expected for a red supergiant. Observations indicate strong surface activity. It remains uncertain how precisely these surface changes connect to the deepest internal stage. The visible surface is still far above the core. It reveals the outer response of the star, not the final state of the center. Here, light leaves Betelgeuse in great quantity, filtered by a surface that shifts like heated gas rather than standing like stone. Bright cells rise, cooler areas darken, molecules absorb some colors and release others. The star's face changes slowly, and each change is carried outward through the atmosphere, into the wind, through the dust, across interstellar space, and finally into the patient instruments on Earth. The visible surface of Betelgeuse changes gradually through ordinary cycles, yet during the period known as the Great Dimming, the change becomes unusually strong. Between late 2019 and early 2020, the star fades to a level far below its normal range. Observers across the world notice the difference. In Orion, the familiar red shoulder no longer competes with the brightest nearby stars. The change develops over months rather than hours. But for a well-known bright star, the decline appears remarkable. Astronomers respond quickly because Betelgeuse is already recognized as a late-stage red supergiant. Since such stars eventually explode as supernovae, any major shift in brightness draws attention. Telescopes on Earth and in orbit begin coordinated observations. Visible light, infrared light, ultraviolet light, and spectroscopy are used together. Historical records of brightness variation are examined alongside fresh measurements. Researchers compare the event with known cycles and with behavior seen in other evolved stars. At first, the cause is uncertain. The fading is too large to ignore, yet not violent in the manner expected from a true stellar explosion. Betelgeuse remains intact. No burst of neutrinos is detected. No expanding supernova shock appears. The star simply dims. Scientific interpretation therefore proceeds carefully. Several explanations are considered together, including surface cooling, dust formation, pulsation, and changes in convection. The event becomes a study in how a red supergiant can alter its appearance without reaching final collapse. Images taken with powerful interferometric systems reveal that the dimming is not evenly distributed across the visible disk. Part of the star appears darker than before. Spectral observations suggest that the photosphere cools during this period. Cooling affects brightness strongly in visible wavelengths because cooler gas emits less visible light, and because molecules such as titanium oxide absorb more effectively at lower temperatures. Even a moderate temperature decrease can therefore reduce visible brightness substantially. At the same time, evidence grows for a dust-related explanation. Observations indicate that Betelgeuse ejects material from part of its surface before the deepest stage of the dimming. As this gas moves outward, it cools. Dust grains likely condense within the expanding material. When the dust cloud passes between Earth and the star, it blocks and scatters part of the visible light. Infrared observations support this interpretation because dust absorbs visible radiation and re-radiates energy at longer wavelengths. The star appears less dim in infrared than in visible light, consistent with dust obscuration. The favoured explanation becomes a combination of both effects. A surface region cools, reducing visible brightness, while expelled material forms dust that further darkens the line of sight. This interpretation matches many of the observations without requiring an imminent supernova. The event therefore demonstrates how dramatic a red supergiant's outer activity can appear while still belonging to ordinary late-stage stellar behaviour. The Great Dimming also reveals how strongly wavelength matters in astronomy. Human eyes see only a narrow part of the electromagnetic spectrum. A star that appears to fade greatly in visible light may behave differently in infrared or radio wavelengths. By combining observations across many wavelengths, astronomers separate temperature effects from dust effects. Dust blocks blue and visible light more efficiently than infrared. Cooling changes spectral signatures in recognizable ways. Together, these clues allow the event to be reconstructed layer by layer. Brightness records from amateur astronomers become especially valuable during this period. Thousands of observers contribute measurements gathered night after night. Though each observation is simple, together they create a continuous timeline. Professional observatories provide detailed physics, while widespread monitoring provides dense coverage through time. Betelgeuse becomes an example of how large scientific institutions and patient sky watchers can contribute to the same understanding. Public discussion during the dimming often centers on the possibility of imminent explosion. The idea spreads rapidly because Betelgeuse is famous and because supernovae capture public imagination. Yet astronomers remain cautious. Massive stars can show extreme variability without collapsing immediately. Observations indicate that the dimming belongs to the outer layers rather than to a detected catastrophic change in the core. It remains uncertain exactly how close Betelgeuse is to final collapse in absolute terms, but the dimming itself is not accepted as evidence that explosion is imminent. The event also encourages closer study of historical records. Earlier fluctuations in Betelgeuse's brightness are compared with modern data. Some patterns appear familiar, though the Great Dimming reaches unusual depth. The star's semi-regular cycles continue through and after the event. Gradually, Betelgeuse brightens again. The return supports the interpretation that the star experiences a temporary surface and dust episode rather than terminal destruction. A true supernova would not reverse in this manner. The dimming reveals the complexity of observing red supergiants. Brightness measured from Earth is not controlled by one process alone. Surface temperature, convection, pulsation, atmospheric motion, molecular absorption, and dust formation all interact. A change in one layer can affect another. The visible result becomes the combined product of many overlapping conditions. Betelgeuse therefore acts less like a simple lamp growing dimmer and more like a vast atmosphere responding to internal motion. The event also highlights the difference between external appearance and internal state. The outer layers can change dramatically while the deep core remains hidden from direct observation. Astronomers infer internal processes from models and indirect signals, but no telescope can see directly into the core of Betelgeuse. The Great Dimming belongs mainly to regions near and above the photosphere. It teaches more about mass loss, dust production, and surface variability than about the exact timing of collapse. After the deepest fading passes, the star resumes its familiar place in Orion. Its brightness rises again, though variability continues. Researchers continue to analyze data gathered during the event, because the observations are unusually rich. The dimming becomes one of the best observed episodes of major variability ever recorded for a red supergiant. It improves understanding of how large stars shed matter and form dust close to their surfaces. The visible face of Betelgeuse remains restless after the event. Light continues to brighten and fade over months and years. Dust still surrounds the star, gas still rises through the atmosphere. The great dimming does not stand apart from the nature of the star. It reveals that nature more clearly. A massive aging star can produce striking visible changes without reaching its final collapse. Observations indicate a powerful disturbance in the outer layers. It remains uncertain how often comparable events occur across the full lifetime of such stars, but the evidence shows that Betelgeuse remains active, unstable, and deeply dynamic at its visible surface. Below the visible changes of the Great Dimming, Betelgeuse continues to follow slower patterns of expansion and contraction. These patterns are called pulsations. A pulsation is a rhythmic change in a star's outer layers, where gas moves outward and inward as pressure and gravity adjust. In Betelgeuse, the rhythm is not perfectly regular. The star belongs to a group known as semi-regular variables, whose light rises and falls in recognizable cycles that also drift, weaken, strengthen, or overlap. The result is a brightness record that looks ordered in some spans and irregular in others. Astronomers have identified more than one timescale in Betelgeuse's variation. One important cycle lasts several hundred days. Another longer pattern extends over several years. These timescales are measured through careful brightness records collected across many decades. The shorter cycle is often linked to pulsation in the outer layers. The longer cycle remains less certain and may involve large-scale surface motion, atmospheric changes, or other processes. Observations indicate that more than one physical cause contributes to the star's changing light. A red supergiant is especially suited to slow pulsation because its outer layers are extended and weakly bound. In a smaller, denser star, gravity holds the surface more tightly and sound waves cross the star more quickly. In Betelgeuse, the outer envelope is huge. Gas takes a long time to move through it. Pressure changes travel slowly across the broad layers. Expansion and contraction therefore occur over months and years rather than minutes or days. The star's size turns internal motion into long, patient variation. During an outward phase, parts of the outer layers move away from the center. The gas expands and can cool. Cooling changes the color and brightness of the emitted light. It can also strengthen molecular absorption in the visible range. During an inward phase, gas may become somewhat warmer and denser. The visible brightness can increase. This description is simplified because the whole surface does not move as one smooth shell. Different regions move differently, and atmospheric layers may lag behind deeper motion. Still, pulsation provides one of the main frameworks for understanding the star's repeated variability. The energy behind pulsation comes from the balance between gravity and pressure. Gravity pulls gas inward. Pressure from hot gas and radiation pushes outward. In a stable star, these forces remain nearly balanced. In an unstable outer envelope, the balance shifts. A layer may expand too far, cool, lose pressure, and then fall inward. Compression can heat it again, increasing pressure and pushing it outward. This cycle does not behave like a simple machine in Betelgeuse because convection, opacity, and mass loss interfere with the motion. The star's rhythm is therefore broad and imperfect. Opacity plays a role in how pulsations affect light. When gas becomes more opaque, it traps radiation more effectively. the trapped energy can push on the layer and help it expand. As the layer expands and cools, opacity may change again, allowing radiation to escape more easily. In some kinds of variable stars, this process creates very regular pulsation. In Betelgeuse, the outer layers are too large and complex for such clean regularity. The principle remains important, but it is mixed with other motions. The several hundred-day cycle has often been measured in visible brightness. It is not always the same strength. Sometimes it appears clearly. Sometimes it becomes harder to distinguish from other changes. The long record shows that Betelgeuse does not behave like a clock. Its brightness contains patterns, but those patterns are shaped by a living star with turbulent gas. Astronomers use mathematical tools to separate possible periods from the data. Yet the physical interpretation must remain cautious. A detected period does not always correspond to one simple movement. The longer variation, lasting several years, has attracted attention because it may be linked to changes beyond ordinary radial pulsation. Radial pulsation means expansion and contraction centered around the whole star. A long secondary period may instead involve large convective cells, atmospheric circulation, rotation, or an external influence. Some recent work also considers whether a companion could affect observed brightness in a repeating way. Observations indicate that Betelgeuse has long-term variability. It remains uncertain which mechanism dominates that longer timescale. Pulsation affects the atmosphere above the photosphere. When outer layers expand, they can lift gas to cooler regions where molecules form more easily. If the lifted gas travels far enough and cools enough, dust may condense. In this way, pulsation can support mass loss. It may not drive the wind alone, but it helps move material outward to places where radiation and dust can continue the process. The surface rhythm therefore connects to the surrounding wind and dust field. Even though each layer behaves differently, the great dimming occurs against this background of pulsation. Some studies suggest that the timing of the dimming coincides with a low point in one of the star's normal cycles, while an additional cooling and dust event makes the fading much stronger. In this view, pulsation creates favorable conditions, and a localized surface event adds an extra effect. This interpretation does not require an approaching supernova. It places the dimming within the star's known habit of expanding, cooling, lifting material and changing brightness. Pulsation also changes measurements of the star's radius. When the outer layers move, the apparent size may vary. However, measuring this change is difficult because the atmosphere is extended and wavelength dependent. The photosphere may shift in one way, molecular layers in another, and dust-forming regions in another. A single radius cannot capture all of these motions. Astronomers therefore compare observations in several wavelengths and use models to identify which layer is being traced. The star's breathing is not a single line moving in and out, but a deep envelope adjusting through many levels. The changing light of Betelgeuse does not mean that it is unstable in a new or unexpected way. Red supergiants commonly vary. Their outer layers are large, cool, and convective. Their atmospheres form molecules and dust. Their winds carry material away. Betelgeuse is especially close and bright, so these processes are easier to observe. Its variability feels dramatic because it is visible to human eyes and because the star is famous. Scientifically, the pulsations fit within the known behavior of evolved massive stars. No observation of pulsation alone gives a reliable countdown to collapse. The outer layers respond to pressure, gravity, convection, opacity, and mass loss. The final collapse depends on the hidden core far inside. A red supergiant may pulsate for a long time before exploding. Observations indicate that Betelgeuse is in a late stage of life and that its outer envelope is active. It remains uncertain how far the core has advanced through its final burning stages. The surface rhythms are real, but they are not a clock for the last moment. Within these pulsing layers, Betelgeuse changes slowly enough to be followed from Earth across seasons. The star brightens, fades, expands, cools, warms, and shifts. Its light carries the record of gas moving through a huge envelope. Each cycle is broad, imperfect, and partly hidden by the atmosphere above it. The rhythm is not a warning bell. It is the ordinary motion of a massive star whose outer body is too large and loose to remain still. Within the pattern of Betelgeuse's changing light, astronomers also examine the possibility that another object may move close to the red supergiant. This possible object is described as a companion. A stellar companion is a star or substellar body held in orbit around another star by gravity. In many stellar systems, two stars form and evolve together. Some are widely separated and easy to distinguish. Others are close enough that their light blends into a single point from Earth. Around Betelgeuse, any companion would be extremely difficult to see because the red supergiant is vast, bright, and surrounded by active gas. The idea of a companion arises from efforts to explain some of Betelgeuse's longer brightness changes. The star has a main pulsation cycle of several hundred days and a longer variation that lasts several years. Some long secondary periods in red giants and supergiants remain poorly understood. They may come from internal motions, large surface cells, atmospheric changes, rotation, or orbital effects. A companion is one possible explanation, not a settled fact. Observations indicate patterns that can be modelled in this way, but it remains uncertain whether the proposed object truly exists. A close companion near Betelgeuse would be hidden inside the overwhelming glare of the supergiant. The brightness difference could be enormous. If the companion is much smaller and hotter, it may contribute only a faint amount of light compared with the red supergiant. If it is cooler or less massive, it would be even harder to detect. Telescopes must separate weak signals from the changing surface and atmosphere of Betelgeuse itself. The task is similar to trying to notice a small lamp beside a vast glowing cloud, while the cloud changes shape and brightness over time. The possible companion would affect observations in several ways if present. Its gravity could disturb gas in the outer atmosphere. Its motion could create repeating changes in the combined light. It might influence dust formation or produce subtle asymmetries. It could also affect measurements of position, because the observed center of light might shift as the system moves. However, all of these effects can also be confused with Betelgeuse's own activity. The red supergiant already has giant convection cells, pulsations, atmospheric flows, and uneven dust. Separating one cause from another requires long, precise monitoring. Some recent studies propose that a companion may help explain a long secondary period in Betelgeuse's brightness. In this interpretation, the companion orbits in or near the extended outer environment and changes the observed light as it moves. It may displace material, modulate dust, or add a small brightness contribution. The idea is physically possible because massive stars can have companions, and many high-mass stars are born in multiple systems. Yet possibility is not confirmation. More observations are needed to distinguish a true orbiting object from internal stellar behavior. The scale of the problem is large. Betelgeuse is not a compact star with a neat boundary. Its visible surface is enormous, and its atmosphere extends far outward. A companion close enough to influence the long brightness cycle might move near regions where gas is already changing. In such a setting, the difference between a companion passing through outer material and a convective feature rising from within can be difficult to identify. Both can produce asymmetry. Both can affect brightness. Both can appear as slow changes in the observed disk. Orbital motion would have a period, meaning the time required for one complete path around the star. If a companion explains a repeated brightness cycle, the orbit must match that timescale within the limits of observation. The mass of Betelgeuse and the distance of the companion from the center would determine the expected orbital period. Because Betelgeuse's radius is so large and uncertain, any close orbit must be considered together with the extent of the star's atmosphere. A companion could lie outside the photosphere but within regions still filled with gas from the red supergiant. A companion could also have influenced Betelgeuse over its earlier life. Binary interaction can change stellar evolution if stars exchange mass or disturb one another's envelopes. In some systems, one star strips material from another or spins it up. For Betelgeuse, there is no settled evidence for strong past interaction of this kind. Its current properties are broadly consistent with a massive star evolving into a red supergiant. The companion idea remains focused mainly on explaining present-day brightness and motion patterns, not replacing the general understanding of the star's life stage. The search for a companion uses several techniques. Precise measurements of position can reveal a wobble if the star moves around a shared center of mass. Spectroscopy can reveal periodic shifts in line positions if orbital motion changes the star's velocity toward or away from Earth. High-resolution imaging can look for faint structures near the star. Interferometry can search for asymmetries in the light distribution. Each technique faces difficulty because Betelgeuse itself is variable. A surface feature can mimic a positional shift. Atmospheric motion can mimic a velocity change. Dust can mimic a dimming pattern. Scientific caution is especially important here. A companion would be interesting, but it would not by itself indicate that Betelgeuse is about to explode. Many massive stars have companions, and many red supergiants show long-term variability. The presence or absence of a companion does not provide a direct measurement of the core's final burning stage. It may explain part of the outer behavior, especially the long secondary cycle. But the supernova timing remains tied to internal evolution that cannot be read simply from an orbital pattern. The possible companion also shows how science handles uncertain signs. Observations do not always point immediately to one answer. A pattern in brightness may have several plausible causes. Models are built and compared. Predictions are tested against new data. If a companion exists, future observations may reveal its orbit more clearly or detect its light directly. If it does not, improved models of convection and pulsation may explain the same pattern without it. The uncertainty is not a failure of measurement. It reflects the complexity of a nearby red supergiant whose surface and atmosphere are themselves active. Within this region of inquiry, Betelgeuse becomes not only a single star but a possible system. The evidence is careful and incomplete. The red supergiant dominates the light, the mass loss, and the visible behavior. Any companion remains hidden, faint, and difficult to confirm. Observations indicate that some long-period changes may be consistent with an additional influence. It remains uncertain whether that influence is an orbiting body or a deep pattern within the star's own outer layers. The search continues within the glow and motion of Betelgeuse, where even a quiet companion would be difficult to separate from the breathing of the star itself. Below the visible surface patterns and possible outer influences, Betelgeuse contains enormous convective cells. These cells are regions where hot gas rises from deeper layers, spreads outward, cools, and sinks again. Convection is one of the main ways heat moves through the outer envelope of a cool supergiant. In Betelgeuse, the scale is immense. The cells may be so large that only a few dominate the visible face at one time. This differs from the Sun, where the photosphere is covered by many smaller granules. Betelgeuse is looser, larger, and slower, so its heat rises in broad, heavy motions. The outer envelope of a red supergiant is well suited to convection because energy moving outward meets gas that can absorb and release radiation in complicated ways. When radiation cannot carry all the energy smoothly, hot material begins to move. A rising parcel of gas expands as pressure decreases. As it expands, it cools. Near the surface, it loses energy as light. Cooler gas becomes denser and sinks back inward. This motion does not require a solid surface or a fixed pattern. It forms in the deep fluid body of the star, where gas behaves like a moving plasma, a state in which atoms are partly stripped into charged particles. In Betelgeuse, these motions occur over distances comparable to the scale of planetary orbits. A convective cell may span a large fraction of the star's radius. The time needed for such a cell to evolve may be months or years. This slow change matches the long variations seen in the star's brightness and surface structure. A bright region on the photosphere may mark hot gas reaching outward. A darker region may mark cooler gas descending, or a place where the atmosphere above has become more opaque. The surface view is therefore a visible trace of deeper heat transport. Computer models of red supergiants show convection as broad, irregular, and turbulent. Turbulent means the motion is complex, with swirling flows of many sizes. In such models, rising plumes can push the photosphere outward, alter the atmosphere, and help lift material into regions where wind and dust formation begin. The models do not reproduce every detail of Betelgeuse perfectly, but they support the general picture of giant cells shaping the star's outer layers. Observations with interferometry also show brightness patterns consistent with large convection. The energy carried by convection begins deeper than the visible surface. Nuclear reactions in inner regions produce energy, but that energy must travel outward through many layers before it escapes as light. In the outer envelope of Betelgeuse, convection becomes a major part of this journey. The gas itself transports heat. A rising column brings warmer material upward, like a slow current in a deep ocean of plasma. The comparison is limited, because stellar gas is extremely hot and diffuse. Yet it helps clarify the motion. Heat is not only radiating through still matter, matter itself is moving. These cells also affect the star's shape. Betelgeuse is often described with a radius, but its outer layers are not perfectly spherical. Large convective motions can raise one region higher than another. They can produce local expansion, cooling, and mass ejection. A red supergiant's photosphere is therefore a moving boundary shaped from within. The surface may bulge slightly in one area, while another area sinks. This unevenness contributes to changing brightness and to the difficulty of measuring a single diameter. Convection interacts with pulsation. Pulsation involves broad expansion and contraction of stellar layers. Convection involves local rising and sinking currents. In Betelgeuse, both occur together. A pulsation phase may lift the outer layers while a convective plume pushes extra gas upward in one region. The combination can produce stronger local disturbances than either process alone. This is one reason a dimming or mass loss event may appear uneven across the disk rather than affecting the whole star equally. The star's outer body is not a uniform shell, but a changing field of currents. The convective cells also help explain why red supergiants can lose mass even though the exact driving mechanism remains difficult to define. Hot gas rising from deeper layers can carry momentum toward the surface. If it reaches high enough, the gas may enter cooler atmospheric layers. Pulsation and radiation may then help move it farther out. Dust formation can add another push. Convection is not the only cause of mass loss, but it supplies large disturbances that make escape easier. Observations indicate that material leaving Betelgeuse is clumpy, which fits a surface shaped by uneven convection. The brightness changes caused by convection are not always periodic. A convective cell can grow, shift, and fade without repeating on an exact schedule. This irregularity appears in Betelgeuse's light curve, the record of brightness over time. Some parts of the light curve reflect pulsation cycles, while other parts reflect changing surface structure. The overlap makes the star semi-regular rather than strictly periodic. In this region, the star's behavior resembles weather more than clockwork, though it is weather inside a stellar envelope rather than in an atmosphere like Earth's. Magnetic fields may also arise from moving charged gas. In stars, the motion of plasma can generate and shape magnetic fields. Betelgeuse has shown evidence of weak magnetic fields at its surface. These fields are much weaker than in some active stars, but they may still interact with convection and mass loss. The details remain uncertain. Observations indicate that magnetic signatures exist, yet their role in shaping the atmosphere and wind is still under study. In a vast convective envelope, even weak fields may mark the motion of charged material. Convection does not provide a direct view of the core. It belongs to the outer envelope, far above the central regions where the most advanced nuclear burning takes place. However, it is an important link between inner energy and outer appearance. Energy made deep inside must pass through convective layers before becoming the light seen from Earth. Changes in convection can alter the surface without indicating that the core has reached final collapse. This distinction remains central to interpreting new signs from Betelgeuse. A surface change can be real, measurable, and dramatic while still being an outer layer event. The convective region is therefore a place of slow internal motion. Heat rises in vast cells, gas cools and sinks, the photosphere shifts above it, the atmosphere responds, dust and wind may begin from material lifted by these currents. Observations indicate that such motion is a normal part of Betelgeuse's present state as a red supergiant. It remains uncertain exactly how each cell forms, how long it survives, and how strongly it contributes to each observed dimming or brightening. The star's outer body continues to turn energy into motion, and motion into light, across scales too large for steady calm. Beneath the convective region, Betelgeuse holds a deep hydrogen-rich envelope. This envelope is the broad outer body of the star, extending across an enormous volume around the smaller and denser inner regions. It is not quiet. It carries heat, responds to pulsation, feeds the atmosphere, and loses matter through the wind. In a red supergiant, the envelope becomes expanded and diffuse after the star has left its earlier stable phase. The gas spreads outward as the inner structure changes, and the visible star grows to a size far beyond its first main stage. Hydrogen remains abundant in this envelope, even though the core has already moved beyond simple hydrogen burning. During the earlier main part of the star's life, hydrogen in the central core fuses into helium. Fusion is the joining of light atomic nuclei into heavier nuclei, releasing energy. Once central hydrogen becomes depleted, the balance inside the star changes. Burning continues in layers outside the core, and the outer envelope expands. Betelgeuse's present red supergiant form is the result of this deeper rearrangement, expressed outward as a vast cool body. The envelope is held by gravity but not tightly at its outer reaches. Its gas is far less dense than material in the core. The farther outward the gas lies, the weaker gravity becomes because of the immense radius. Pressure and radiation support the layers against collapse, while gravity pulls inward. This balance is not exact in every place or at every time. Pulsation and convection disturb it. Some material rises high enough to join the atmosphere and wind. Other material sinks back inward. The envelope is therefore both a storehouse and a source of motion. The mass of Betelgeuse remains uncertain within a range. Estimates depend on distance, luminosity, temperature, rotation history, and evolutionary models. It likely began with many times the mass of the Sun, and it has already lost some of that mass. The present envelope contains a large share of the star's remaining outer material. How much remains affects the future appearance of the eventual supernova, but the exact amount is not directly measured. Observations indicate ongoing mass loss. It remains uncertain how much mass the star has lost across its full red supergiant phase. Inside the envelope, temperature and pressure increase with depth. Near the outer layers, gas is cool enough for molecules to influence opacity. Deeper down, molecules cannot survive, and the gas becomes hotter and more ionized. Ionized means atoms have lost some electrons and become charged. The envelope gradually changes from cooler outer gas to hotter inner plasma. There is no hard wall between these conditions. The change occurs across depth, shaped by gravity, radiation, and motion. Energy moves through this envelope in more than one way. In some regions, radiation carries energy outward as photons are absorbed and re-emitted many times. In other regions, convection carries energy through moving gas. The importance of each method depends on temperature, density, and opacity. Betelgeuse's expanded envelope favors deep convection in its outer parts. The moving gas connects the hidden interior with the visible surface, though the connection is indirect and slow. Energy may take a long time to work its way through the star before it appears as light. The envelope also contains the memory of earlier internal mixing. Massive stars can bring material altered by nuclear reactions toward their surfaces. Convection and other mixing processes change the chemical composition of the outer layers. Astronomers study surface abundances, meaning the relative amounts of different elements, to infer how much processed material has been mixed upward. In red supergiants, nitrogen may be enhanced and carbon may be reduced compared with earlier stages because material affected by hydrogen fusion has reached the surface. These clues help identify the star's evolutionary history. Mass loss removes part of the envelope over time. The wind carries material away from the outer edge, but the supply comes from deeper layers that move upward. If mass loss is strong enough, it can reduce the envelope significantly before the star collapses. For some massive stars, losing much of the hydrogen envelope changes the type of supernova that later appears. Betelgeuse still shows the character of a red supergiant with a substantial cool envelope. Observations do not show that the envelope has been stripped away. It remains a large, defining part of the star. The envelope responds slowly to changes below. If inner burning stages alter the star's energy flow, the outer layers may take time to adjust. Because the envelope is huge, it can smooth, delay, or transform signals from deeper regions. This is one reason surface behavior is not a simple indicator of the core's exact state. A change deep inside does not immediately appear as a clear sign at the surface. The envelope acts as a broad buffer, absorbing and reshaping internal changes as they move outward. The star's rotation also affects the envelope. Though Betelgeuse rotates slowly at the surface compared with many younger massive stars, Measurements of rotation are difficult because the surface is large and changing. A star may also rotate differently at different depths. If Betelgeuse once rotated faster or interacted with a companion, its envelope may carry some trace of that history. Present observations indicate broad motion and possible rotation, but convection and pulsation complicate the picture. The envelope is not a rigid spinning body. It is a moving gas layer with many overlapping flows. The pressure in the envelope is tied to the star's expansion. When the inner regions contract after hydrogen core burning ends, energy production in surrounding shells increases and the outer layers expand. Expansion cools the surface, shifting the star toward red light. The envelope becomes large because the internal balance has changed. Betelgeuse's present appearance is therefore an outer expression of deeper structural evolution. The red colour and large radius arise from the expanded envelope, not from a cool or weak star overall. The envelope remains central to the question of visible signs. Dimming, brightening, dust formation, wind changes, and surface patches all occur in or above this region. These signs are important and measurable, but they are not direct messages from the core. The envelope is thick, active, and able to produce strong variability on its own. Observations indicate that Betelgeuse's envelope is unstable in the ordinary sense expected for a red supergiant. It remains uncertain exactly how its present mass, mixing, and internal motion set the timescale for the final stages. In this deep outer body, Betelgeuse holds much of what still makes it visibly a red supergiant. Hydrogen-rich gas stretches across a vast radius, heat moves upward, currents rise and sink, pressure waves pass through wide layers. Some gas eventually escapes, while the rest remains bound in the star's broad envelope. The envelope is not the centre, but it is the great surrounding weight through which every inner change must pass before becoming light. Inside the deep envelope, closer to the hidden centre, Betelgeuse contains burning shells where nuclear fusion continues in layers. These shells are not visible from outside. They are inferred from the physics of massive star evolution and from the observed properties of the star. A shell is a region around the core where a particular fuel can still fuse. After hydrogen is depleted in the central core, hydrogen burning can continue in a layer around the helium-rich center. Later, helium and heavier elements can burn in deeper layers as the star advances. In a massive red supergiant, the interior becomes structured by these stages. The outermost important burning shell is hydrogen burning. In this region, hydrogen nuclei fuse into helium, releasing energy that supports the star and contributes to its luminosity. The process is not identical in detail to the Sun's dominant hydrogen fusion. In massive stars, the carbon-nitrogen-oxygen cycle is especially important. This cycle uses carbon, nitrogen, and oxygen as helpers in turning hydrogen into helium. The result is still helium and released energy. The shell lies far below the visible surface, but its energy eventually moves outward through the envelope. Deeper inward, helium burning becomes central during a later stage. Helium nuclei fuse to form carbon and oxygen. This stage requires higher temperatures than hydrogen burning. In a massive star, helium burning lasts much less time than the earlier hydrogen burning life. The pace of stellar aging quickens because each later fuel stage releases less energy per unit mass, and because the star becomes more luminous. Betelgeuse's red supergiant state indicates that it has moved beyond central hydrogen burning. The exact current burning stage inside remains uncertain, because the interior cannot be observed directly. As massive stars evolve, they may develop an onion-like arrangement of layers. The comparison is useful only for structure, not for stillness. Different fuels burn in different shells, with lighter elements generally burning farther out and heavier elements deeper in. Hydrogen can burn in an outer shell. Helium can burn deeper. Later stages may involve carbon, neon, oxygen, and silicon in the innermost regions of the most massive stars. Each stage requires higher temperature and pressure than the one before. Each stage also occurs over a shorter time. The final stages can be very brief compared with the whole life of the star. For Betelgeuse, models must decide which of these stages is active now. Observations indicate that it is late-stage massive star, but they do not reveal the exact condition of its core. Some models place it in helium burning, while others allow more advanced interior evolution depending on its initial mass, rotation, mass loss, and mixing. The outer appearance alone cannot settle the matter. A red supergiant can spend a long time in a state where its surface looks broadly similar, while its interior changes substantially. The burning shells are therefore central to the uncertainty about timing. Energy from these shells does not travel outward in a simple straight path. Photons created or released in deep layers are absorbed and re-emitted many times. Convection may carry energy through some regions. The journey outward can be slow and strongly altered by the envelope. A change in a burning shell may not immediately produce a clear surface sign. This is why brightness changes at the photosphere must be interpreted with caution. The outer star can vary because of surface and atmospheric processes without requiring a sudden change in shell burning. The burning shells also change the chemical structure of the star. Hydrogen burning increases helium and alters the balance of carbon, nitrogen, and oxygen in processed material. Helium burning creates carbon and oxygen. More advanced burning stages create heavier nuclei. Some of this material may remain deep inside until the final explosion. Some processed material from earlier stages may be mixed upward into the envelope before then. The surface composition of Betelgeuse gives indirect evidence of internal mixing, but it does not expose the deepest products of advanced burning. The pressure in these inner layers is much greater than in the envelope. Gravity compresses the gas as depth increases. Temperature rises because compression and nuclear reactions heat the material. Fusion can continue only where the temperature and density are high enough. If a region becomes depleted of one fuel, it contracts and heats until another fuel may ignite deeper inside, if the star is massive enough. This pattern drives the star through successive stages. The outer envelope responds by expanding, cooling, and becoming luminous as a red supergiant. Shell burning is also connected with neutrino losses. Neutrinos are very light particles that can escape dense stellar interiors easily. In advanced burning stages, neutrino emission carries away energy rapidly. This makes the final stages of massive star evolution proceed quickly. However, neutrinos from Betelgeuse's ordinary pre-supernova burning are far too weak to provide a simple public warning at present distances with ordinary monitoring. A strong burst of neutrinos would be expected at core collapse itself, but that belongs to the final event rather than the long shell burning life before it. The shells are not perfectly smooth. Convection can occur around burning regions, mixing fuel and ash. Boundaries between layers may shift. Rotation may stir material. Waves generated in deep regions may move outward. In some models of late-stage massive stars, vigorous burning can create internal waves that carry energy toward outer layers. Whether such processes produce observable effects before collapse depends on many details. For Betelgeuse, observations of the surface do not yet provide a confirmed sign of such a direct deep event. This interior structure explains why certainty is difficult. The stars outside is observable in rich detail, but the burning shells are hidden behind a vast envelope. Models use known physics, measured luminosity, temperature, radius, surface composition, and variability to infer the inner state. Different reasonable assumptions can lead to different timelines. Observations indicate that Betelgeuse is evolved and will end as a supernova on astronomical timescales. It remains uncertain whether its interior is still in a relatively longer burning stage or nearer to shorter final stages. Within the burning shells, Betelgeuse is no longer the young massive star it once was. It has consumed central hydrogen and rearranged itself into deeper layers of fuel and ash. Fusion continues in regions wrapped around the core, adding energy to the envelope above. The shells do not announce their exact state at the surface. They work under great pressure, in darkness hidden from direct view, shaping the star from within while the outer layers slowly brighten, dim, expand, and lose matter. At the innermost hidden region of Betelgeuse lies the core, the dense centre whose exact present condition remains uncertain. No telescope can see this region directly. Light from the core does not travel outward freely through the star. It is absorbed, scattered, transformed, and delayed by the layers above it. The core is therefore known through physics rather than direct sight. Astronomers build models from mass, luminosity, temperature, surface composition, variability, and the general theory of stellar evolution. These models agree that Betelgeuse is advanced in life, but they do not give a precise date for collapse. The core is the place where gravity becomes strongest, and where the deepest burning stages occur or have occurred. During the star's early life, the core fuses hydrogen into helium. After central hydrogen is exhausted, the core contracts and heats. Later fuels can ignite if the mass is high enough. In massive stars, this sequence moves through helium, carbon, neon, oxygen, and silicon burning before an iron-rich core forms. Iron is important because fusing iron into heavier elements does not release useful energy for support. Once an iron core grows too massive to resist gravity, collapse begins. For Betelgeuse, the exact stage within this sequence is not known. Observations indicate that the star is a red supergiant and that it is near the end of massive star evolution, compared with its total lifetime. It remains uncertain whether the core is in a longer-lasting helium-burning phase or a more advanced, shorter phase. This distinction matters greatly. Helium burning can last far longer than later stages, carbon, neon, oxygen, and silicon burning happen on much shorter timescales in massive stars. The outer appearance may not clearly separate these possibilities. The uncertainty comes partly from the star's initial mass. Betelgeuse likely began with many times the mass of the Sun, but estimates vary. A somewhat different initial mass changes the internal path. Rotation changes mixing. Mass loss changes the weight of the envelope above the core. A possible companion could affect the history if interaction occurred, though this remains unsettled. Each factor changes how quickly the core develops and how much fuel remains. Models can be physically reasonable and still differ in timing because the starting conditions are not known exactly. The present luminosity of Betelgeuse gives an important clue. A star's luminosity is closely linked to the mass and structure of its core. In evolved massive stars, the core largely determines how much energy the star must carry outward. The observed luminosity therefore helps constrain evolutionary models. Yet luminosity itself depends on distance, dust, temperature, and the distribution of light across wavelengths. Since these quantities carry uncertainty, the inferred core state also carries uncertainty. Careful measurement narrows the range but does not remove it. The core is much smaller than the star's visible body. Betelgeuse's photosphere extends across a vast radius, while the inner burning regions occupy a much smaller central volume. The difference in scale is extreme. The star appears huge because its envelope has expanded, not because the core itself is large. The core is dense, hot, and hidden beneath the great weight of surrounding gas. This contrast makes the red supergiant form visually dramatic but physically layered. The largest visible part is not the region that decides the final collapse. As the core evolves, it loses energy in part through neutrinos. Neutrinos escape easily from dense matter and carry energy away. In late burning stages, neutrino losses become strong and help accelerate evolution. This means the final internal changes of a massive star can proceed rapidly, while the surface remains broadly similar. The envelope may not have time to show a simple warning pattern before collapse. A star can look like a red supergiant until the central support fails. This is one reason surface dimming, brightening, or dust events must not be treated as a countdown. If the core eventually forms enough iron group material, pressure support fails. Electrons and atomic nuclei are forced into new states as gravity overwhelms the center. The core collapses inward extremely fast. A rebound and the action of neutrinos help drive the supernova explosion in current models, though the details of the explosion mechanism remain an active field of research. This final process belongs to the future state of Betelgeuse, not to a confirmed present event. Observations available now do not show that the collapse has begun. A future collapse would first become detectable through signals that can escape the star. Neutrinos from core collapse would leave before much of the visible light from the explosion emerges. Gravitational waves might also be produced, though detectability would depend on the event and instruments. Light would follow as the shock moves outward and breaks through the surface. These are physical expectations for a core collapse supernova. They are not current detections from Betelgeuse. No such confirmed pre-explosion signal has been observed. The core's state is also constrained by the fact that Betelgeuse still behaves like a red supergiant with a large hydrogen-rich envelope. Its surface variability, wind, and dust are consistent with such a star. Some evolved massive stars shed their envelopes and become hotter, stripped stars before exploding. Betelgeuse has not shown that transformation. It remains cool and extended. This supports the view that, whenever it explodes, it may produce a supernova associated with a hydrogen-rich outer envelope, though the exact type depends on how much envelope remains at that time. The phrase "about to explode" can be misleading when applied to a star. In human speech, it suggests hours, days, or years. In stellar evolution, a star may be near the end and still remain tens of thousands of years from collapse. It may also be closer than that, but current observations do not fix the interval. The best scientific statement is careful. Betelgeuse is expected to explode someday as a core collapse supernova. Observations do not show that this event is imminent in a confirmed human timescale sense. The unknown core prevents a precise answer. The hidden center therefore holds the deepest uncertainty in the star. The outer layers are observed changing, the wind is measured, dust is imaged, the photosphere is mapped, pulsation is tracked, the core remains inferred. It is the region where the final decision belongs, but it is also the region least open to direct observation. Models continue to improve as measurements improve, yet no model turns Betelgeuse into a predictable clock. Inside this uncertain core, gravity, heat, fuel, and ash define the future. The star's outer signs raise scientific questions because they reveal activity in the surrounding layers. They do not reveal the exact hour of collapse. Betelgeuse remains a massive red supergiant with a hidden center moving through late stellar evolution. What is known is large and careful. What remains unknown is the precise inner stage and the time still left before gravity finally wins. At the center of the question about Betelgeuse lies the physical condition required for a core collapse supernova. A massive star does not explode simply because its surface grows dim, its atmosphere sheds dust, or its outer layers pulse. It explodes when the central support of the core fails. Gravity then overwhelms pressure in the deepest region, and the core collapses. The outer star responds only after that inner failure begins. This order matters because most visible signs from Betelgeuse come from layers far above the center, while the final event depends on a small, dense, hidden core. The final readiness for collapse develops only after nuclear burning has built an inner structure that can no longer gain support from fusion. Earlier fuels release energy when they fuse into heavier elements. Hydrogen becomes helium. Helium becomes carbon and oxygen. Later stages in massive stars can create neon, oxygen, silicon, and iron group material in the center. The star survives each stage as long as pressure from heat, radiation, and particles can resist gravity. The balance grows more fragile as the fuels become heavier and the stages become shorter. Iron marks a special limit. Fusion of iron group nuclei does not release energy in the way earlier fusion stages do. Instead, it requires energy. When an iron-rich core becomes too massive, it cannot support itself by ordinary fusion. Electrons are forced into protons, forming neutrons and neutrinos. This removes pressure and allows collapse to accelerate. The inner core falls inward at enormous speed. The process is deep, brief, and hidden until signals escape. Betelgeuse has not shown a confirmed sign that this collapse has begun. It remains visible as a red supergiant with changing brightness, a broad atmosphere, a wind, dust, and pulsation. These features are consistent with late massive star evolution, but they are not proof of immediate failure at the center. Observations indicate that Betelgeuse will eventually end as a supernova. It remains uncertain when. The range may be long on human timescales because the exact core stage is unknown. A supernova from Betelgeuse would be safe for Earth at its estimated distance. It would become a brilliant object in the sky, likely visible in daylight for some period depending on the details of the explosion and surrounding material. It would not be close enough to destroy Earth's atmosphere or life. The event would be scientifically extraordinary because it would occur in a nearby well-studied red supergiant. Instruments would record neutrinos, light, spectra, and changes in surrounding gas. Yet this remains a future expectation, not a present observation. The newest signs that raise questions are therefore signs from outer and middle layers. The Great Dimming shows that Betelgeuse can eject material, cool unevenly, and form dust that blocks visible light. Changes in brightness after that event show that the star remains variable. Reports of possible companion effect show that long cycles may have more than one cause. Measurements of surface motion show giant convection and pulsation. These signs improve understanding of the star, but none provides a verified countdown to collapse. The phrase about to explode requires careful meaning. In astronomy, a star can be near the end of its life and still remain for many thousands of years. A human lifetime is short compared with most stellar processes, even late ones. The final burning stages of a massive star can be short, but identifying those stages from the surface is difficult. Betelgeuse could be closer to collapse than many stars, because it is already a red supergiant. That does not mean its explosion is expected tonight. This year, or within a confirmed near future? Scientific consensus remains measured. Betelgeuse is an evolved massive star. It is losing mass. It varies in brightness. It experienced an unusual dimming caused mainly by surface cooling and dust. It may have additional influences that are still being tested. It is expected to explode someday. Observations do not establish that the explosion is imminent. This is the steady conclusion supported by current evidence. The center of Betelgeuse remains concealed beneath the envelope. Models continue to improve as distance estimates, surface maps, spectra, and long-term brightness records improve. Each new observation narrows some uncertainty and reveals new complexity. The star is close enough to study in unusual detail, but not close enough for its interior to be seen directly. The final answer depends on physics inside a region that no image can reach. When collapse eventually begins, it will not need to announce itself through a slow visible fading. The core will fail first, neutrinos will escape, a shock will move outward, the outer layers will respond as the explosion develops. Until such signals are detected, the observed surface changes remain part of the known life of a red supergiant. They are meaningful, but they are not final. At the innermost region of the topic, the calm answer is that Betelgeuse is ready in the broad evolutionary sense, but not known to be ready in the immediate sense. It has reached a late stage where a supernova belongs to its future. It has not provided evidence that the future has narrowed to a predictable human date. The star continues to shine, dim, pulse, lose matter, and carry its hidden core through the last great phases of massive stellar life. In the quiet after the center, Betelgeuse remains a star of measured uncertainty. Its red light continues to cross space, carrying signs from layers that rise, cool, darken, and brighten. Around it, dust drifts outward from material once held in the star's loose envelope. Above its surface, gas moves through an extended atmosphere. Beneath its surface, broad currents carry heat. Deeper still, hidden burning layers shape the star's long final state. Nothing in the present evidence requires sudden alarm. The star is old for a massive star, but young compared with quieter stars like the Sun. It has lived quickly because great mass spends fuel quickly. Its future supernova belongs to the natural order of massive stars. Yet the time of that event remains beyond precise knowledge. Observations indicate activity, mass loss, and deep evolution. They do not show a confirmed immediate collapse. From Earth, Orion keeps its familiar form through the seasons. Betelgeuse marks one shoulder with a soft orange-red glow, sometimes brighter, sometimes fainter. Its changes are real, and they are watched with care. Each measurement adds a small piece to the understanding of how massive stars age and return matter to space. The star rests in sight, not still, but steady enough for patient study. Its outer layers breathe across months and years. Its dust moves slowly into darkness. Its hidden center remains beyond direct view. The sky holds the evidence gently, and the question remains calm, open, and scientific.